I welcome you to this lecture of microscale transport process. What we have been discussing in the last class was electric double layer. Let me give you a quick briefing on what we have already discussed, since there was a gap in between. This solid surface acquires surface charge when brought into contact with an electrolyte liquid due to several reasons. Those reasons are given there. Deprotonation or ionization of surface groups, that is very common. So, just because a solid surface and there is an electrolyte in the proximity, there would be some surface charge developing. Okay, and net surface charge density at the liquid solid interface is a function of local pH, because you know what pH is. It is basically hydrogen ion concentration log of that. So it is very much related to the pH of the system. Full deprotonation at pH greater than 9. Now, once there is a surface charge acquiring, once these charges are acquiring on the surface, are acquired on the surface, then there would be opposite charges getting attracted, and this is forming an excess of mobile ions near the interface with charge opposite to that of the wall. Okay, and this is referred as electric double layer. These excess charges can be used to impart a force on bulk fluid through ion drag. So, the counter ions, they reside in compact layer next to the wall, which is referred as Stern layer, which is in adsorbed state. The other one is the counter ions that reside in a more diffuse layer next to the wall, where the ions are free to move. So, what we discussed in the last class, or we started discussing in the last class, is that the potential at the shear plane, the boundary of the liquid flow problem, is called Zeta potential. Okay, and there is something called a Debye length, and this we discussed in the last class. Let me point out quickly what we had. We had derived few things in the last class. Let me just point out the basic findings there, the basic equations there. First of all, we are working within the framework of Navier-Stokes equation, which appears like this. What we mentioned in the mentioned previously is that these terms we are all familiar with. Okay, del T v is the derivative with respect to time, and v dot delta v, you know what we are talking about here. This is the pressure gradient term, eta is the viscosity, so and rho g is the component due to gravity. So, this part you are familiar with, and this rho ELE we introduced recently. This is the body force term arising from this ion drag that we talked about. So, we have this additional body force term present. Now, what we said in the last class is that these delta this rho ELE, these needs to be, we need to understand this term well, and we need to see how this term is getting affected because of this electric double layer. Now, what we have derived in the last class is something like this, that del square phi r, that is equal to 2 z E epsilon naught E c naught z E c naught divided by epsilon, this is c naught sine hyperbolic z E by kb t phi of r. This is an expression that we had obtained in the last class. Okay. Now, here we said that for the limit z e zeta much less than kb t, when this is happening, okay, this is referred as Debye Huckel limit. When this is happening, when this is happening, in that case, these sine hyperbolic can be you can make an approximation here that sine hyperbolic u is equal to u when u is small. So, that is exactly what you are doing here. So, with this what we have found in the last class is and this is coming from Taylor series expansion and ignoring the other higher order terms. What we ended up with in the last class is del square phi, which is for a one dimensional case this would be equal to del square phi z del z square, that is equal to 1 by lambda d square phi z. All right, 1 by lambda d square phi z. All right. Now, this is an expression that we had, okay, and this expression we said that here this lambda d is referred as d by length. And what is this phi now? Phi was basically electric field. This phi is nothing but E is equal to minus delta phi, where this E is this E that is appearing in the Navier-Stokes equation. So, E is equal to minus delta phi. What is E? E is the electric field. E is the electric field and this phi is the potential. This phi is the potential. So, that is how this phi and E they are related, and with the phi we had this expression where lambda d is equal to the d by length. This is the case. So, this is very straightforward, and once you solve this equation, solution of this equation would be pretty straightforward. It is referred as or I can write this as phi z is equal to zeta exponential of minus z by lambda d. Well, what you can say is, I mean, this limit that we put here, basically this z e phi has to be much less than k b t. Now, but phi at what point, that would be the question people will ask. I mean, what phi at what z we are referring to. So, instead of putting phi at any arbitrary value, we put it as zeta. Zeta is the value of phi at z is equal to 0. That means, if you plot phi versus z, then it should be dropping, and the value here at z equal to 0, that is referred as zeta, commonly referred as zeta potential. Phi is the potential, and with distance from the wall, this phi is decreasing. So, at the bulk, electric double layer does not have any effect, any existence. So, phi is decreasing. Okay. So, now this decrease is the way this is decreasing, this is given by this function phi z is equal to zeta exponential of minus z by lambda d, where z is the distance from the wall, phi is the potential which is decreasing, and at the wall, that means at z equal to 0, phi is equal to zeta. This is the expression that this gives. So, this is the expression we have. So, this expression came assuming this d by Huckel limit, that is assuming z e zeta much less than k b t. Now, this is probably a very hypothetical kind of limit. Instead of that, people are more familiar with a limit zeta much less than 26 millivolt at room temperature. That is what people are generally familiar with, this sort of limit. Okay, instead of putting things in symbols, you can put things in numbers. So, this is what you have. This is the expression that you have. What type of situation this is simulating? This is simulating a wall which has acquired some charges and the counter ions it pulled, and this expression gives you the potential as a function of distance from the wall. Now, what you are assuming is that at z equal to infinity, phi is 0. Probably that is what was one of the boundary conditions you have used. You have used phi infinity is equal to 0 and phi 0 is equal to zeta. So, these are the boundary conditions you have used. Now, the problem in hand that we have is a channel. We are talking about a micro channel, we are not talking about a simple wall. So, if you have a micro channel, this we were discussing at the end of the last class, that if you have a micro channel, that means if you have two walls, one wall here with counter ions accumulating, another wall here with counter ions accumulating, and both are pulling the bulk of the fluid. Now, this part you refer as bulk, this part you refer as the bulk of the fluid, and this bulk of the fluid is dragged by this body force. Okay. So, if that is the case, then you can use the same expression, only your boundary condition will change, right. That is something which I remember I was discussing at the end of the last class, that the boundary condition will change. So, what would be the new boundary condition in this case? The new boundary condition would be that phi is equal to phi plus minus h by 2, that is equal to zeta, okay, plus minus h by 2. That means, you are your center here your center was at the wall, I mean the earlier case, but in this case the center is, if this is the channel, then the center lies here. Okay. So, at plus h by 2 and at minus h by 2 you have this the value of potential is zeta, and the other thing is that at the center there is symmetry existing. So, d phi dz is equal to 0 at the center by symmetry. So, this is the new boundary condition you have, but the governing equation remains same. I mean, we do not have any reason to believe that a governing equation should change. So, with these two boundary conditions, you remember in the last case also we came up with this expression, phi z is equal to C 1 e to the power z by lambda d plus C 2 e to the power minus z by lambda d. Okay. So, in that in the earlier case we said that since at z equal to infinity phi has to be finite, rather phi has to be equal to 0. So, this C 1 has to be equal to 0, that was our rationale to put C 1 as 0, but here the situation is different, it is phi plus minus h by 2 is equal to zeta. So, that means you have C 1 as well as C 2 both non-zero. Okay. So, you have to work it out, and what you would get in that case is equal to zeta cos hyperbolic z by lambda d divided by cos hyperbolic h by 2 divided by lambda d. Right. So, in that case what you would have is rho E L z. What is rho E L z? You remember we have already obtained this expression, you need to go back and see how we have written it. Del square phi is equal to minus rho E L z, rho E L by epsa. So, this was an expression we had worked with earlier. So, accordingly this rho E L z would be equal to minus epsa zeta cos hyperbolic z by lambda d divided by lambda d square cos hyperbolic h by 2 divided by lambda d. All right. So, this is the expression you have for rho E L z. Now, if you come up with a scheme, which is something like this, you have a channel, okay. You have electrode here, this is the electrode and this is another electrode, they are connected. Okay. This is the way it is. Now, if we are interested here in a velocity profile, if we would like to know what would be the velocity profile because of this presence of these electrodes, because electrodes are required to create a velocity, create a potential gradient, and because of this potential gradient we expect that a flow will take, we expect because of this potential gradient we will have this term appearing, rho EL into E. This becomes instrumental, and so there would be a velocity even if there is no pressure gradient. Suppose this delta P is not there. If delta P is not there, we know that there will not be any flow, but if by some way we can put this velocity, we can put a delta phi here, by some means we can put a delta phi here, some means we can make this term non-zero, then we can induce a velocity, and we are interested to know what would that velocity be in the micro channel, in the channel where we have two walls. So, if this is the scheme, we would like to know what would be this velocity profile. So, for that we need to solve the Navier-Stokes equation with this understanding, with this being phi, with this being rho, and we have appropriate E. With this we need to solve the Navier-Stokes equation. So, that is exactly what I would be taking up next. So, let us draw this once again. This is an electrode, this is another electrode. Okay. This direction is x, this direction is z. All right. This direction is z, and you have phi external at z x equal to 0 is 0, p external at x equal to 0 is equal to 0. Here the phi external at x equal to L, all right, at x equal to L, that is equal to delta V, and p external at x equal to L is equal to 0. So, that means there is no pressure drop. We are expecting that just because we have put this potential gradient, we should expect some velocity happening because of this Navier-Stokes equation, because of that body force term. So, this is what we need to solve here. Now, if now there would be this, where is this dy layer in this case? I know that there would be a dy layer. What is that lambda d? This is lambda d, right? Here the lambda d lies. Here also there is a lambda d. This is this lambda d is the dy length, right? We have defined this lambda. We have defined this dy length earlier. Okay, so here the charges are all accumulating. I am not drawing the charges again, plus or minus, because that would confuse. Now, what was the equation we had at that time? We said the equation was rho del T V plus V dot delta V, that is equal to minus delta P external plus eta del square V minus rho EL EQ delta phi external. Now, whether it is minus or plus, that depends on what charges you have here and the direction of this field, in which direction you are putting the field. Okay. So, here it needs to be minus because of the charges that you have, because what you have in this case is the E external will be in this direction. If somebody plots the rho EL EQ, it would be in this direction, and the velocity profile would be in this direction. So, the velocity would be in this direction. the bulk flow will be in this direction, whereas the potential would be in this direction. All right. So, that is how this sign of this is defined. Now, if you solve this for a one dimensional case, it would be something like this. I mean, let me write the equation first, and then I find out what all assumptions we have taken here. This is the equation that we have for one dimension with the assumptions. What all are the assumptions? Zeta potential is constant along the wall. Electric field is homogeneous. Flow is at steady state. And d by length is much smaller than the half width of the channel. So, what you write here is E here is equal to minus E Ex hat, because E is in negative direction. This electric field is external electric field is applied in negative x direction. Delta phi external is equal to minus E, that is equal to E Ex hat, that we already know. And the other thing is that the velocity term V, velocity is equal to V x, which changes with z, E x hat. So, V at any position is, it is V x which changes with z, E x hat. That means velocity is only in the x direction, there is no other component. Okay. And delta p external is equal to 0, that we already assumed. So, with these assumptions and with these understanding, you ended up with this expression, Navier-Stokes in one dimension. So, once we know that, then probably it would be easy to write this expression in a more compact manner as del z square V x z plus epsa E divided by eta phi E q z. This quantity is equal to 0. That is exactly what we had in the last slide. If you see, this is the expression we have. So, instead of writing it this way, you take this del z square and put everything within del z square. All right. So, it is the derivative. So, basically del square this whole thing del z square, that is equal to 0, that is what you say. And you know the boundary condition here. Boundary condition here is that V x at plus minus h by 2, that is equal to 0, because we assumed that at the wall, whether it is upper wall or the lower wall, the Stern layer is existing. So, it is all adsorbed and there is no velocity, that is firmly attached to the wall. So, at the wall V x is equal to 0, this is the boundary condition you have, and this is the governing equation you have. This is the governing equation you have. Of course, there would be some symmetry at the center, that is always there. I mean, if you need to, you can use that as boundary condition as well, or it will follow automatically. Now, this is the governing equation and this is the boundary condition. The solution to this equation would be V x z, that is equal to zeta minus phi e q z into epsa e divided by eta. This is the solution to this equation, solution to this governing equation with this boundary condition in place. Now, if you want to now what is phi z? What is phi z? If we look at this phi z, if we bring in those earlier slides where we just introduced it, what was the phi z we had at that time? You remember we were trying to find out how would the phi z look, how the potential changes, right? We have been trying to find out in the beginning of the class how the potential changes, and we said if we have simply a wall and extending this electric double layer, simply the bulk extends to infinity, just only one wall, we had this expression with lambda d being the dy length and phi would change with z like this. Then we said if we have two walls, then we have the bulk in the middle and we have electric double layer present here as well as there. Okay, and then we said that the governing equation for phi remains same in that case, and the boundary condition will change. This is the boundary condition at plus minus h by 2, this is equal to zeta, and at the center symmetry exists. So, this is what we said was the case with phi, the potential, and then we came up with this expression for the potential. Phi is equal to zeta into cos hyperbolic this divided by this. So, this is the case for a channel, this is the case for a single wall, right. So, this is the case for a channel. So, we said the phi will follow this expression. So, now we intentionally we developed this expression for phi because we know this phi would be handy here. Here what did we do? We put the body force term in the Navier-Stokes equation and solved it for one dimension, and by solving this for one dimension with this boundary condition that at the wall the velocity is 0, with this boundary condition we came up with this expression. Now, we need to replace this phi because phi does not, this phi will come from here. All right. So, this phi we have intentionally we developed this phi for a channel with two walls to be used as part of this expression, because our final aim at the very outset I said is to obtain a velocity profile, first thing, and second thing is to find out how much flow. We have two issues here when it comes to electroosmotic pumping. We have basically two issues. One is that how much velocity, how much average velocity you can generate. Suppose I put this pump in place, how much velocity it can generate when there is absolutely no pressure gradient existing, but still simply by electroosmotic flow you are generating so much of velocity. That is one issue. Second issue is, I mean, immediately you will question is where will you get such ideal situation that there is no pressure drop. I mean, if you are pumping something, then there would be a back pressure, you would be pumping against a back pressure. So, up to what back pressure it can deliver the fluid, because if the back pressure is beyond a limit, then there will absolutely be no flow. Okay. So, if we have a back pressure, then how would be the velocity profile and what would be the flow rate. Okay. Now, what we are doing now is we are obtaining the velocity profile with the assumption that pressure at x equal to 0 and pressure at x equal to L both are 0. P external at x equal to 0 is 0, P external at x equal to L is equal to 0, and phi external, this is 0 here and this is delta V here. All right. So, with these condition we are coming up. So, this is the first case we are solving. Later on what we will do is, we instead of putting it 0, we will put some pressure here, put some back pressure here. That means, you are pumping against a back pressure, and then we would like to know what would be the velocity profile. Okay. So, first case no pressure, we are close to getting the velocity profile. This is the velocity profile we obtained, and this phi eq has to be replaced by this expression that we have already gotten. We have already gotten for a two wall system, for a channel system, not a single wall system. For a 2 wall system, this is the expression that we already have. So, if we bring in that expression there, so then the Vx z would be equal to 1 minus cos hyperbolic z by lambda d divided by cos hyperbolic h by 2 divided by lambda d. H by 2 is the half aperture into epsa zeta divided by eta into E. This is the expression you have for the velocity profile. See, I have a z term here. This z term is changing. Z is equal to 0, where if this is the channel, I am having an electroosmotic flow taking place through this channel. Z is equal to 0 here, Z is equal to plus h by 2 here, Z is equal to minus h by 2 here. So, within this framework, the velocity is velocity, I have a velocity profile, okay, and this velocity profile is expression for this velocity profile is given by this expression. Now, if you ever get a chance to plot this, I mean, you can plot this, you can take some sample values and you can plot Vx just the way we have plotted for Poiseuille's flow, we have plotted parabolic velocity profile and all. So, if somebody wants to plot this expression, what he will end up with seeing is that the velocity profile looks like this. It is pretty much flat, and there is a minor change. I mean, it has to be 0 here. So, from 0 to the final value, that happens within a short distance. That happens within a short distance. That is the trend of this expression. So, this is pretty much flat, and if somebody wants to know what is this velocity, he will find, probably you can check with the limit as well, it will come out that way, that this part of the velocity, this v, this is actually referred as EO, VEO, electroosmotic velocity, which is epsa zeta divided by eta into E. So, this is predominantly this is the velocity over the most part of the channel, and near the wall the velocity changes from here to 0. So, for all practical purposes, not for all practical purposes, I mean, you can if somebody wants to know what is electroosmotic velocity for quick calculation, you can use this expression. This is pretty much the electroosmotic velocity, which is constant for most of the cross section. Okay, look at the parameters that is involved here. Epsa, zeta is that Zeta potential of that electrolyte wall, that system. You have a solution, you have ions moving around, and you have developed some Zeta potential on the wall. It is that zeta. Eta is the viscosity of the fluid, okay, which is just simply coming because you have that Navier-Stokes equation, and there you have eta del square v term. So, this eta is coming from there. E is the electric field that we imposed. So, this is the electroosmotic velocity that you have. So, if somebody wants to find out what would be the electroosmotic velocity under certain situation, so he needs to use this formula. And if he needs to know really how the profile would be, and if he is asked to draw precisely what the profile would be, then he needs to resort to this expression. All right. So, this is what you have as far as the this electroosmotic velocity is concerned. Now, the issue here is that we have assumed here that this, as I said, phi external is equal to 0, p external is equal to 0. Now, what we will do is, this is delta v, this is fine. Here instead of 0, we would put this as delta p. That means, we will try to find out if it has to act as a pump, it has to act against a back pressure. That is the idea, right? You have to pump the fluid through a channel, you have to pump the fluid through certain media like this. So, that media or that channel will impose a back pressure, okay, if the outlet of the channel is say open to atmosphere. But to get the flow going through that media, you need to overcome some back pressure. So, instead of 0, we need to put this as delta p. Okay. So, in that case, this del p term in Navier-Stokes equation, we had this del p term earlier. This del p term was not used at all. This del p term was not used at all in the Navier-Stokes equation. Now, what we will do is we will use this del p term in a sense that these del p term would be this minus delta p external. Now, we will have minus delta p external, that is equal to then it will have a value, it will be minus delta p by L E x hat. So, this is something which you would be imposing. So, if we impose this, what would be the velocity profile? That is what people would be looking at. Now, before I get into the expression part of it, because this again we will have several symbols. Before we get into this, on the side of this plot, I would like to draw how the velocity profile would be. I mean, can you think about it? How would the velocity profile be in such case? That here there is no back pressure, but in this case there will be a back pressure. You will be surprised to see that the velocity profile in this case would be like this. Basically, this part you are following the electroosmotic flow, because this here you have charges and this charge is trying to drag the fluid. Because of this ion drag, there is the bulk fluid is also dragged with the ion, and all these things are happening. So, it would be just like this velocity near the wall. However, you have a back pressure, and this is acting like a simple parabolic velocity profile in the opposite direction, because you have a p there and you don't have the p on this side. So, you have this kind of trend. So, this would be the velocity profile that we are looking at, and with this velocity profile, now you need to know how much delta p, against how much delta p this electroosmotic pump can still work. All right, because you have a pump in place and you need to know you are pumping it through a media, and that media would give a back pressure of so many Pascal, so many atmosphere, so many such and such. So, you need to know whether the pump can deliver that kind of pressure or not, otherwise this pump will not work. So, we need to solve this velocity profile, and we need to find out when this velocity is, what is the limiting value, when this velocity is 0, that is the limit. So, when does that limit reach, when is that limit reached, and what is the corresponding back pressure. So, you know that is the back pressure that the pump can still pump against that back pressure. Okay. Beyond that, pump will fail. So, for that we need to know the velocity profile. So, with this understanding, let me point out that this expression would be, here we would be looking at the Navier-Stokes equation would be something like this. The Navier-Stokes equation would be eta del square V x z plus ifsa del square phi e q z delta v by L minus delta P by L. This is the expression that you have. All right. This is the expression that you have, and typically the solution here, I mean this system of equation that allows you to get a solution which is basically superimposed, called superimposed velocity. The velocity that is arising from pressure and the velocity that is arising from electro-osmotic flow. So, the sum of these two, so it would be like this: 1 minus cos hyperbolic z by lambda d divided by cos hyperbolic h by 2 divided by lambda d into epsa zeta divided by eta. I am not writing it as E, instead of this I am writing it as delta V by L, because that is easier to understand, minus this part is the pressure component, h by 2 whole square minus z square 1 by 2 eta delta P by L, delta P by L. All right. So, this is the component which is arising from pressure, and this is the component which is arising from electroosmotic velocity, and this is the combined Vx(z), and if this Vx(z) is plotted, you will get the profile which we have shown here in this case. Okay, you will get this kind of profile. Now, we are not very much, I mean profile is fine, we have intuitively also we knew that that is the profile. What we are interested in at this point here is two things that I mentioned in the beginning itself. Two issues are, two concerns are here. One is electro-osmotic flow at 0 back pressure, and the other point is back pressure needed to exactly cancel the EO flow. There are two issues here. I mean, you must appreciate that these, one is that 0 back pressure, what is the electroosmotic velocity you have, electroosmotic flow you have, and the other is up to what back pressure it can still have an electroosmotic flow, beyond which the flow will stop. Okay, so, from the design point of view, if somebody is going to use this pump, these two factors are immensely important to him. Now, if we pick up some standard values, for example, if zeta is equal to 0.1 volt for a cylindrical channel with radius is equal to say 0.01 millimeter, okay, for length is equal to 0.1 millimeter, eta is equal to 10 to the power eta is equal to 10 to the power minus 3. What is the viscosity of water? Minus 3 Pascal second, and if the epsa is equal to, say you take some value of say 100 epsa naught, okay, you get about this electroosmotic flow. This electroosmotic flow would be about 0.2 nanoliter per second per volt, and this back pressure would be 5.5 Pascal per volt. That means you apply 1 volt of delta V across this electrode, you get this much of flow and you get this much of back pressure. Beyond this back pressure, the flow will stop. So, naturally this scheme does not seem to be a very attractive proposition, because the flow rate is pretty small and the pressure also it can stand is very small, you must appreciate. So, there is a way out. I mean, people who are using this electroosmotic pump, they are not using a single channel. They have overcome this problem and they have used this pump successfully with the flow rate that we expect typically in a microchannel system. What they do is they use several channels, not just single channel, and by several channel I mean you can have a porous medium. That means you can have beads, several beads packed inside the channel. You have a larger channel, and within the channel you have several beads, so that you have multiple parallel channels operating simultaneously, and that can overcome this problem. All right, because this would be evident if you look at this problem itself. I mean, if you look at the expression, if you have large number of channels, then this problem can be circumvented. This problem you can get away with this problem, and in fact you can have the pressure drop to the tune of, say, then you can have the flow rate to the tune of microliter per second, pressure drop several kilopascals. So, these are very much possible with a channel with either with frits or closely packed glass spheres. Okay, so that you can generate large number of parallel channels. That is there. So, any electroosmotic pump would become comprised of such frits inside the channel, or the channel will be packed with beads, so that you can have several parallel channels operating. I will see if we need any clarification on this issue, we can probably discuss this in the next class. Otherwise, the next topic that I will pick up is electrophoresis. Next topic that I will be picking up is electrophoresis. So, if I quickly look at what we had in this PowerPoint slide, is that we have discussed about the potential at the shear plane, the boundary of the liquid flow problem, and which is called Zeta potential. D by length we discussed, which is lambda d basically. D by Haeckel limit we discussed. This all our analysis is based on, the entire analysis is based on d by Haeckel limit. That means the sine hyperbolic u is equal to u. That we had the Taylor series expansion, we ignored the higher order terms with that understanding. So, that is the d by Haeckel limit. Single flat plate and parallel plate geometry, that I think we understood by now, that in one case we have simply that one plate and we have the phi changing with z, and in another case you have two plates at z equal to plus h by 2 and z equal to minus h by 2, that we have looked into, and the velocity profile under electroosmotic flow, that we have already established. The next topic that I am going to pick up is basically electrophoresis, Electrophoresis, electrophoresis once again, I mean this is induced drift motion of colloidal particles. I had a definition of electrophoresis at the very beginning, you remember. Electrophoresis is induced drift motion of colloidal particles or molecules suspended in liquids due to an electric field. So, what we have is, we have an electrode here, we have another electrode here, and we have a particle. Okay. We have a particle here. Now, this particle has certain charge in this, and you have already imposed an electric field. You have imposed an electric field E, and this particle has charge Q. So, if the particle is small, then the force that is exerted here, that would be equal to Q into E, and that force would be imposed on the particle if these are connected. If these are connected, that force would be imposed on the particle. On the other hand, if this particle has to move because of this force, there would be drag imposed on the particle, because if it is in the liquid, if this is the particle moving, so then there will be a drag force. So, there will be a balance between these two forces. Okay. So, we would be discussing in the next class what would be the velocity of this particle if the particle is small. Okay. Small in the sense the particle is small and it has a huge d by length, because this particle, there would be a formation of d by length, formation of an electric double layer around it, or the particle is big. This is the particle and you have a small double layer forming around it, okay, and then this would be pulled. So, what would be the velocity this particle will acquire? So, if you, the idea of this electrophoresis at the very outset we mentioned is that if you have particles, several such particles of different size or charge, okay, and these particle would be attracted to the electrode by different forces. So, if you hold this under this electric field for some time, you will see that particles of same size and charge, they will be accumulating in one band. Particles which could not flow at that velocity, they will not be, they will be at some other place. So, you will be having some kind of classification within the body of this material. So, that classification we are looking at, that is what we would be calling electrophoresis. Now, what we would be doing is we would be taking these two cases separately in the next class, and we will see how we define force and how we define the velocity in this case, and what would be the utility of this whole scheme. This is very good to find out what particles you have. This particle could be a cell, biological cell. This particle could be a clay particle. There are particles of different sizes and charges that can be classified using this technique. I have that is all I have for today's class. And I will try to see if there is any outstanding question on this electroosmotic flow. I will try to address them in tomorrow's class. That is all I have for today. Thank you.